So I think we are almost 5 minutes into the hour. So thank you for coming to the Deep Learning Committee of Practice meeting. Today we have a great presentation from Natasha Shakes. She's working, sorry, at Google as a research scientist. She have done incredible work on combining RL and curriculum learning and many other interesting research that I have been following, at least personally, over the last couple of years. And she have been very, very honored to take this time and share with us her latest research. And so we are very, very happy to have you here. And please go ahead, Natasha.
Thank you so much. Yeah, and I'm hoping we can keep this like pretty interactive. So I've got lots of material, but just I think interrupt me and we can talk about anything if you have questions or thoughts. I think that'll be a lot of fun. So I was asking before I came, basically how many people in the audience are already familiar with kind of the concepts behind reinforcement learning. So I don't know how teams work, but are you guys able to like raise your hand if you kind of get it or?
We have a raise feature in Teams. So
okay.
Yeah, I guess I did raise the hand now, so.
Oh, nice. Okay. Awesome. All right, so I'm getting 2 people raising their hand, but then that seems like the majority maybe need a quick refresher on RL or would benefit from.
Yeah.
Okay. All right, let's go into it. So the whole idea behind RL, or why I think it's important, speaking of large language models and RL, there's controversy whether, let's say, if you want to train a language model, you should need RL. But I think the reason it's important is, unlike traditional learning methods, what RL is trying to do is optimize for the total expected future reward across a sequence of actions. So instead of just optimizing the decision you're taking now, you're saying I can do something that's going to be less good in the short term, but it's going to pay off in the long term. So like this total expected future reward over an episode is the key quantity that you're trying to optimize. And you're doing this via trial and error learning. So you're in some environment state S, you try to take an action A, you observe how well it pays off in terms of the reward, and you continue to optimize this. And you're learning this policy pi. So this is just some notation I might use later. I want to make sure you guys are on the same page. The other notation is I'm probably going to talk about this Q value, which is estimating that key quantity, like the total expected future reward. And it's basically saying, if I'm in state S and I take action A, what's going to be my reward for the rest of the episode? Like the total reward over time for the rest of the episode, if I continue to follow my policy. So that's something that's a good quantity we want to note. Of course, I'm interested in deep reinforcement learning, which just means I'm estimating the policy of the agent with a neural network. And of course, you guys probably know there's been a lot of famous deep reinforcement learning successes. They can beat the world champion at Go, we can play video games, and it's quite promising, perhaps, to be able to use deep RL for things like robotics. But it also has a lot of issues. And, people say that unlike, say, computer vision or NLP, deep reinforcement learning hasn't really had its moment yet, like it's AlexNet or its transformer moment, right? So why is that? Well, I think there's a couple of key problems. One is computational complexity. So even the more efficient version of AlphaGo, which was AlphaGo 0, had to play 5 million games of Go to reach proficiency. So like 560 years of human playtime. So it's very sample hungry. And part of that is like there's high variance, and estimating that long-term quantity is difficult. But the other issue is that deep RL often fails to generalize to even slight modifications of the training environment. So the joke is that RL is the only machine learning area where you can train on the test set, right? But what that paradigm leads to is RL algorithms that are overfit to their training environment. And when you try to take them to even a slight thing outside the training environment, it just breaks down. So I think these are some key issues. What my research is asking is, what could social learning do to help address these issues? Now, what the heck do I mean by social learning? Basically, I mean learning from other intelligent agents in your environment. And probably those agents are also learning, right? So you're in this multi-agent system, there's other agents that are smart that are running around. How can you benefit from that? Well, humans and animals are very able to use this Even this 1-inch fish can use social learning when it's dumped into a dangerous new environment to look at where the other fish are gathering to find a safe source of food. Birds can do this too. In the UK, birds learn to open milk top bottles not by individually discovering it each time, but by using social learning to pick up this behavior from other birds. And a lot of writers and authors have argued that humans, the key to our cognitive development and our amazing cultural and technological evolution is that we actually take social learning to the next level. That's our key differentiator. So it seems like a pretty powerful mechanism. What could it do for RL? Well, I mean, some of the benefits are quite obvious, right? Individual exploration is super expensive and time consuming. Like if I wanted to try to invent the Large Hadron Collider by starting with the technology of rubbing two sticks together to make a fire and randomly exploring, I mean, that idea is just laughable. I'm never going to do that within one lifetime, right? And yet, that's actually how we train our RL agents right now. We do trial and error with random exploration. So we have this little walker randomly wiggle until it discovers how to walk, right? So what are we doing? Meanwhile, like individual exploration is dangerous. So if I want to generalize to a new environment that I've never seen before, social learning is a great way to figure out what's a safe thing to do. And if you don't use that and you just randomly explore, you could have problems. So I actually managed to find on the internet a picture of a robot being run over by a car. I was very happy with this. The idea is that if you deployed an RL agent into an environment it hasn't seen and takes the wrong step, it could be in danger. Whereas, of course, if it did something like following where the humans are walking, it's going to be able to restrict where it explores to be safe. So basically, my hypothesis is this learning from other agents can help agents learn more complex behavior, adapt more easily to new environments, so addressing these issues with RL, obviously improve human AI interaction if you're able to better understand and coordinate with the human that you're talking to, and ultimately coordinate better with other agents. So that's kind of what I'm going to be talking about today. The first project I'm going to be talking about is by request when I was invited to give this talk, and it's about training agents to be able to coordinate better with each other. Then I'm going to launch into some new work that uses multi-agent training basically as a tool to improve the learning and generalization of a single RL agent. So basically showing how social learning is just this powerful learning mechanism. Then I'm going to talk about social learning from agents and humans that are just in your environment, that are not necessarily deliberately trying to teach you. And if we have time, I can talk about how to learn better from humans by recognizing their social or emotional or affective signals. This is a lot of my PhD work. But again, just interrupt me. Whatever you think is interesting to talk about, we can just chat. I don't have to get to all of this. So let's start with the multi-agent coordination stuff. So in this project, I wanted agents to be able to learn coordination socially, but train independently. So at the time we were working on this, a lot of the multi-agent coordination algorithms that are out there rely on centralized training and decentralized execution. And I didn't want to do that. So the idea we had was to give agents this intrinsic social motivation or this extra reward for having a causal influence on the actions of other agents. Now, why this? Well, okay, if I'm just looking at how I affect other agents' actions, then I don't need to have a centralized controller and I don't need to observe the other agents' rewards. So I think this is a lot more realistic when we think about applications of multi-agent RL, such as autonomous driving, right? Like the Tesla car can't observe the Waymo car's proprietary reward function, but it can observe whether it turned left, right? So this seems like it's a more realistic way to do multi-agent coordination. And why am I talking about causal influence? That seems weird. Well, as we'll show, this is equivalent to rewarding the mutual information between agents' actions, and we have the hypothesis that this is an inductive bias that will lead towards learning coordinated behavior. All right, so how do we do this? What we want to do is we want to actually start with our standard deep RL agent that's perceiving the environment, it has an LSTM, and it's outputting a policy and a value function. And we're going to augment that with a supervised model of other agents. And what that's going to do is it's going to predict how every other agent is going to act in the next time step, conditioned on what I'm doing and what the other agents are doing in the current time step. And what that allows this agent to do is ask itself counterfactual queries. It can basically plug in some alternative action that it could have taken in the past and predict how that would have changed the other agent's behavior. So it can say, what do I predict agent B would have done if I had taken this other action instead? And doing that, you can sample a bunch of counterfactual actions, plug that into your model, sum over them, and get sort of the marginalized policy of the other agent. So what agent B would do if it wasn't really considering the action of agent A. And the divergence between the probability of agent B's action conditioned on agent A's action versus the marginal probability of agent B's action is actually the causal influence of agent A's action on agent B's action. So, it doesn't actually, if you don't believe me that it's causal, we can check out this causal diagram. We know that causality can't travel through an unconditioned on collider node like this state t+1. So the only path is a causal path. But whether it's causal, in a sense, kind of semantic for this work, what we actually care about is what we're going to do with it. So we're going to give this objective as a reward to agent A. So agent A is going to get a reward if it takes an action that causes agent B to change its behavior. It leads to a change in B's behavior. Why is this cool? Well, we can show that it's actually related to this mutual information quantity. So you can see the influence reward here. The mutual information would require, summing over the probability of the state and the probability of agent A's action. But of course, as you randomly sample many trajectories from the environment and from A's policy, in effect, you're doing that. So in expectation, the influence is a mutual information between agents' actions. So you can think of a really common intrinsic motivation you might have heard of to try to train RL agents when they don't have reward is called empowerment. And that's where the agent maximizes the mutual information between its action and the future state. In this case, we think of this as a form of social empowerment, to make that analogy. But I'm going to stop and ask, does anyone see kind of an obvious issue with this objective? So we're asking agent A to take actions that cause agent B to change its behavior. Would this always lead to coordination? What's the issue? Yeah.
Oh, I thought someone was right. So, I mean, it depends which way would change the behavior, right? So, I mean, it depends I mean, you can have some ill feedback cycles, right? That might interact in a negative way instead of in a positive way, right?
Exactly. So I could easily, just stand in your way, and I've caused you to walk around me, but I haven't helped you. I've influenced you in a negative way. I think we have a hand up.
Right.
Yes, I guess they might go into competition as well, I guess. If they are trying to, if one is changing and let's say if the other has a different agenda, they might compete or something like this. I guess this could also be a problem.
Yeah, they could be competing to influence each other. They could be influencing each other in negative ways. So it's not clear that just from this definition, this should always necessarily lead to coordination. We think, when you are coordinating, let's say we're playing soccer and I'm passing you the ball, then we should have high mutual information between our actions because we are coordinating. But when we're competing, we could also have high mutual information, right? So it's not clear that this should necessarily lead to coordination. All right, so to address this, in this work, we take two measures. The first is that we actually test this in environments where coordinating or really cooperating is exactly the hard problem. So we're looking at these sequential social dilemma environments. The first one, called Harvest, is basically a tragedy of the commons environments. So the agents are trying to eat these little green apples, that gets them reward, but if they eat the apples too quickly, they become depleted and they won't grow back. So all the agents will have less reward if the agents are too greedy, right? Similarly, in this cleanup environment, in order to get the apples to appear, they have to do some work to clean this river. But each environment is partially observable. So when you're cleaning the river, you can't even see if apples are appearing. Other agents can easily be hiding out there and stealing the fruits of your labor, basically. So if you don't believe me that they're social dilemmas, I can make this a bit more concrete. So what we're looking at here are shelling diagrams where they're showing the payoff that you can expect to get if you're following a defecting strategy, like greedily eating too many apples, versus cooperative in blue, given the number of other agents that are cooperating out of 5, right? So if you're on the far right of the graph, everyone's cooperating. If you're on the far left of the graph, no one is cooperating. And what you see is that at almost every stage, you can get more payoff by defecting on your fellow agents than cooperating, right? But if everyone defects, then everyone's payoff is lower. So it's very hard for RL agents to learn this type of complex strategy, and actually we show that, the vanilla agents don't do well in this environment. So here what we're measuring is the collective group reward, how well everyone is doing with the baseline, which is in blue. And then we do see that when we add this influence reward, the agents are able to coordinate better and achieve much higher scores. But how is this possible? We just said influence doesn't necessarily lead to coordination, so why did that work in this case? Oh, and I should mention that this is actually getting a higher score than previous work, which did allow access to the other agents' rewards, so it's quite promising. But we want to figure out why it's actually working. So in this movie, the purple agent that's holding still here is the only one that's been trained with the influence reward. And you can see it behaves a little differently than the other agents. So when there are no apples in green, the purple agent stays still while the other agents keep searching. So why is it doing that? Well, it actually learned to only ever move when an apple is present, and it only ever uses 2 moves when navigating the map. So basically, it only moves when there's an apple, otherwise it stays still. So why does this allow it to gain influence? Well, let's take a look where it's actually had some influence over this yellow agent. So the yellow agent can only see what's in this red box, okay? At this moment, the purple agent chooses to move towards this green apple, which it only does when there is an apple. So why do you think this allows it to gain influence? So it only ever uses 2 moves to navigate the map. It will not move unless there is an apple. So if it does move, its move is a pretty reliable signal that there is food. So what that's doing is it's showing this yellow agent that there's food outside of its field of view, and that's changing its intended behavior. Does that make sense?
So yeah, I think that makes sense. But I thought that the yellow agent should seen the purple agent, right? So I guess what I'm saying is that if the yellow agent see that the purple agent is moving, then he said, "Whoa, there is food there, right? So I should go there." But if he doesn't see it, then cannot influence my behavior, except that I see him moving, right? That I guess.
Yeah. So the thing that's not mentioned here, which is a very good point, is the agents are sort of like always yelling what actions they're taking. Like you can always get their action as input, even if you can't see them in your field of view. Yeah. So that's how good point. I should remember that next time I'm giving this talk. Here's another example where this happens. The pink agent is cleaning the river. It can't see if any apples have appeared as a result of its work. They haven't. When the purple agent chooses to stay still, it signals that there are no apples, and again, it gains influence. So in summary, it's basically using its actions to communicate and thus influence other agents, which we found quite interesting. So of course, the next thing we did was we said, okay, let's train an explicit communication protocol with this influence reward. So we equip the agents with now a discrete symbol communication channel, so they can have a new policy that decides which of a set of symbols to emit that will be put on this cheap talk channel. Everyone else can see it in the next time step. The reason it's cheap talk is because they can just ignore it. There's no reason they have to listen to this extra input. We train the communication policy with the influence reward, and specifically, you get a reward if your communication message influenced another agent's actions. Now, they're only learning actions in order to optimize their own selfish environment reward. So we have a hypothesis that the only way to gain influence is to communicate useful information that helps the other agent optimize its environment reward, right? Because otherwise it would just ignore you. So that's our hypothesis, but we should point out that, learning cheap talk between self-interested agents is a very hard problem. So theoretically, we can show that as agents' interests diverge, the level of information passed on a channel should go to 0. And empirically, there's many results to show like learning these type of communication protocols is hard. But we do see when we train with the influence reward, the agents not only cooperate more effectively yet again, obtaining better group rewards, but they also learn more meaningful communication protocols in the sense that they relate to what the agents are doing in the environment, what their observations are. So you can check the paper for more details on the metrics we developed, but essentially, this is the cool part. So if you plot the degree of influence between an influencer agent on the column and the agent being influenced on the row, what you see is that the agents that are more easily influenced, or essentially like better listeners, if you will, tend to get higher environmental reward. And we found this as a very consistent finding across hundreds of hyperparameter settings in both environments. And what we think this shows is support for our hypothesis that influential communication is benefiting the listener by passing useful information that helps them optimize their environment reward. So I do want to mention in the discussion, as we discussed, whether this action influence is pro-social, in other words, it helps the other agent, is going to depend on the environment. So we think in our environment, the reason that they learn to gain influence by communication is it's a cheap way to influence other agents while still pursuing your own reward. So if I had to spend all my time like standing in your way to get you to move, I'm not going to be picking up very many apples. But this might be the trade-off where I can influence you but still optimize for my own objective. And then we do think that influence via self-interested agents via communication on this cheap talk channel should benefit the listener, so it should be pro-social in that sense. But there's a caveat. Can anyone imagine a caveat? Like why? How could I influence you via communication in a way that doesn't benefit you, even if you're just selfish?
I mean, if you are selfish, definitely communicating and using, I mean, trying to mislead you on something that, right?
Exactly. So exactly, you could lie, right? I could just say, hey, there's an apple over there, go look for it. Meanwhile, I steal all the apples that were over here.
Right.
But that won't work if the agents are interacting repeatedly, because then you would lose influence with me because you would damage your reputation. Yeah. So that's the key thing there. All right, so in conclusion, we think of social influence as this unified method that can promote both coordination and communication in multi-agent settings. And the key contribution, I would say, is that it does allow agents to learn coordination while training independently. So unlike a lot of prior work in this space, it doesn't require access to other agents' rewards or a centralized controller. So that's nice.
That's super cool.
Thanks. Did anyone else have questions? I'm happy to pause for questions on this.
Yeah, I have a small question. Regarding the generalization, if individual agents learn how to communicate better, like what would you do when you throw the agent into an environment where he doesn't have anybody else?
That's a great question, actually. And it's not really something I address in this work, but it is something I'm going to address in the very next talk. But yeah, like this work is basically the agents are always training with their same, 5 buddies, and they learn how to communicate with each other. I would not expect them to be able to communicate with a novel agent. Yeah.
Quick question.
Oh, thank you.
Yeah. So, like, did you find any evidences that the agents have learned to lie? No.
We didn't see that. No. Presumably, like you could try lying, but then you would lose. It would stop paying off.
Oh, okay.
So, yeah.
Yeah. So I guess that for me is a quick question about the kind of environment that you have, because maybe there is. I mean, basically, what's the motivation for lying, right? So if the environment, stimulate or is highly motivate you to lie, then that might have a different kind of outcome. I guess that.
Well, in a sense, the agents in these environments are competing. So, like, if you don't pick up an apple, then I can. So I actually want you to pick up fewer apples, right? So there is a motivation to lie, but I guess in this case they were able to overcome that because you would have to weight the influence parameter correctly,
Right. Yeah, that's interesting. That's very interesting.
You mentioned that the primary agent was limited to do 2 steps the moment it saw an apple. What's the importance of that threshold? Why was it set?
So we didn't restrict it to only using 2 actions. I think the reason that it did that is, like, if you think about this actual mutual information quantity, like I want to maximize the mutual information between my action and your action, then I basically want to have, like, if you think about it, like a one-hot matrix where if I do this action, you're definitely going to do this action. If you think of the confusion matrix, I'm not explaining this very well, but essentially I want to really reduce the number of actions that I'm using to make it very clear what you should do. it's a consequence of the mutual information, basically.
Great, thanks.
Okay. All right, I'm going to go into the next work, which does explicitly address generalization to your previous question. All right, so in this case, previously we're in a multi-agent system. We want agents to learn to coordinate with each other. Now we want to use multi-agent as a tool to improve the learning and generalization for a single agent. So I'm going to come back to this issue about generalization in deep RL. I think it's a big problem. You might think that people have addressed it. So you've probably seen like the OpenAI Rubik's Cube hand, right? So what they did is they say, okay, I want to transfer generalize to the real world, and I only have an imperfect simulator. So let me just randomize the parameters of my simulator and train on that massive random distribution in the hopes that the true parameters in the world will be covered by that distribution, right? And that seemed to work pretty well. But I'm going to set up the case that it's not going to be a viable strategy for a lot of problems. And I'm going to show that with this example. So in this simple environment, we're training this blue agent. It's partially observed. It's trying to walk to this green goal. And we could use domain randomization to randomly generate a bunch of these environments where they randomly place the blocks in the goal in the start state, and the agent has to navigate them. But what's interesting, if you do that, we find that the resulting agent actually generalizes really poorly even to this simple 4 rooms environment, which has walls. And so basically what's happening is, even though you could sample walls within the random distribution, it's just very unlikely that you end up doing that. Most of the mass of stuff that you're sampling is going to look more like this unstructured environment on the left. But you actually care about the agent having specific abilities, like being able to generalize to a structure like walls. So it tends not to work very well in this way. And the other thing is, like, okay, maybe let's say you really believe in domain randomization for robotics, and you say, I'm going to build a simulator of stairs, and I'm going to randomize the height, the width, the texture, everything, and I'm going to train on the simulator. And then I'm going to get a robot that, when I deploy to my house, it's able to walk up this particular set of stairs. Well, now let's say I want to take that technique and train robots that could do package delivery in anyone's house. Well, there's a problem. Like, the real world has a lot of variability. These are actual stairs that you probably didn't simulate, right? So how's your agent going to generalize to those? So what we really want is to be able to have a set of complex training environments that do cover these unknown real-world challenges that I might be faced with. But we don't want to have to program all of them ourselves by hand, right? That's just going to be brittle. I can't anticipate everything. The agent is going to be error-prone. So this is not the right solution. Feel free to interrupt if you have questions too. So one thing you might think that you want to do is say, okay, I'm going to introduce another agent. I'm going to call it an adversary. It's going to design the environment in order to challenge the agent that I'm training. So it's going to design environments that are cases where the agent fails. It's going to find those stairs that my agent can't climb. But does anyone see a potential problem with this?
Yeah, well, I'm cheating because I read the paper. So I will let someone else respond.
The video is going to give you a clue.
Have a mode collapse.
Mode collapse could be a thing. I think I'm going to actually argue against mode collapse, because let's say I'm minimizing your performance and okay, you could do that. But maybe you could say a bit more detail. Let's say that it was an environment that it is possible for the agent to eventually learn to solve. If I keep posing that and you do eventually solve it, then my reward as the adversary is going to go to 0, right? Like, if I continuously pose the same task over and over and over until you figure it out, then it will stop paying off. But what's a case where that can't happen, where I can keep getting I can keep getting rewards forever from posing the same?
You mean as the adversary or as
the adversary? Yeah.
Oh, so just like block the agent?
Exactly, block the agent. And that's exactly what happened in this. So if I make the environment impossible, then I can mode collapse onto something that's going to pay off forever, right? And so this is just going to waste computation. Like, this poor little agent can never get a reward. It can't learn anything. We're just wasting time. So this is not the right objective either. So what we really need is a more elegant way to constrain the adversary so that it can't create impossible environments. But I don't want to do something really domain specific. Like I could say, oh, there has to be a shortest path between the start state and the goal in a grid world. But that's only going to work for grid worlds. So we want something that's more flexible and more general. And ideally, we want to be able to tailor those environments to the current skill level of the agent. So we want to get an automatic curriculum to help the agent learn. So of course, I've been saying, oh, multi-agent is the answer to everything, social learning, social learning. So the solution I came up with was like, let's just add more agents to this problem. So that's actually the idea behind this algorithm. What we do is instead of just having an adversary agent design an environment for a player agent, we're going to introduce a second agent that's going to play the same environment. And we're going to use that to constrain the adversary. So we're going to rename this little player. Let's call him a protagonist. We're going to introduce a second agent called the antagonist. And then the adversary's objective is actually to maximize the regret, which is the difference between the performance of the antagonist and the performance of the protagonist. So essentially, it now is being asked to make environments where it's possible to do well, because the antagonist score should be high, but it's still exploiting the weaknesses of the protagonist to make it more robust. So it's still choosing environments where the protagonist performs poorly. So we call this protagonist-antagonist induced regret environment design. Huge mouthful. The acronym is paired to stand for how this pair of agents is being used. Michael Dennis is my co-author on this paper. He noticed this amazing connection to the decision-making under uncertainty literature. So basically what you can do is show that each of these environment design algorithms map back to a principle of the decision-making under ignorance literature. So domain randomization is the principle of insufficient reason. The minimax adversary is obviously the maxi-min principle. And paired is minimax regret. And these are all forms of unsupervised environment design, which is this formalism we introduced to unify these different algorithms. And what we do to show this is we say, instead of just having a normal POM-DP, which is this RL formalism, we're going to talk about an underspecified POM-DP, which just introduces a new set of parameters. And so you can think of like a UPOM-DP as being the space of all possible grid worlds. But when you give an assignment to this parameter theta, that specifies the actual grid world. So it gives, for example, the locations of the blocks and the goal. And you can talk about how to define a policy that defines a distribution over how to set those parameters. And depending on how you define that policy, you recover these different methods and potentially many more. So that's this unsupervised environment design formalism. The proof that paired is the minimax regret algorithm basically relies on assuming that the adversary and the antagonist are a team, and therefore they can collaborate. And then it becomes a zero-sum game between their team and the protagonist. And you can show that if that game reaches the Nash equilibrium, then the protagonist should be playing the minimax regret policy. We have a proof in the paper that relaxes this assumption, so if you're curious, I'd encourage you to check it out. Does anyone have any questions so far?
I don't know if it's clear that based on the regret, you are avoiding, the previous case. I know that was clear because, you can, I can get, well, at least based on the previous equation. I mean, the paper described everything in detail, but at least based on the previous equation, the protagonist can have, maximum or performance, and the antagonist can have zero performance. I still have a high regret, correct? Or the other way around. I don't recall
other way around.
The other way around, right?
The naming is confusing, but yes, exactly.
Yeah. So there, what I could do, what will happen if I trap the protagonist, right? But the antagonist keeps solving problems, and so maybe there, I guess that what we find out. Maybe what you find out is that it can solve problem, but it's at a slower rate. Instead of you have some regret, like real regret between both, but I'm not sure.
Yeah, so I think a key assumption we're making, and I have a better answer to that question actually on the next slide, but I do want to highlight a key assumption we're making is that, like, if you spend infinite compute training on the same environment that it is possible to solve, then eventually the protagonist would also solve it, right? Because it just got enough samples in that one environment, and we know it is possible to solve. But I will highlight this, which I think is really cool. We think regret is actually a really good objective for getting this curriculum, because here's my claim. Regret is going to incentivize the adversary to create the easiest possible environment the protagonist cannot yet solve, given a simple assumption, which is that your score will be higher if you complete the task in fewer time steps, which is true for almost every environment. That's true in the grid world, it's true in Mujoko, blah, 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 blah. And so what that does, okay, so let's say I'm trying to minimize the protagonist's reward. So basically the right-hand side of my equation is 0. I've succeeded, I've minimized it. So now I'm just trying to pick out of all the environments the protagonist can't solve, which one I should pose. If the reward is going to be higher for getting it done in fewer time steps, then the reward of the antagonist is going to be higher for a simpler environment. So basically, your regret of failing to do an easy task is higher than your regret of failing to do a hard task. It's obvious, right? So what this means is that the adversary is going to continue to propose tasks that are the easiest possible the protagonist can't solve, or basically I'm borrowing some, developmental psych terminology. It's like in the protagonist zone of proximal development. So it's this like nice curriculum objective. All right, so just to make it crystal clear what the paired algorithm actually is, we randomly initialize all the agents. By the way, the protagonist and the antagonist have the same architecture. They're just different weights. And then until convergence, the adversary is going to generate an environment, theta. Both the protagonist and the antagonist are actually going to collect several trajectories in that environment. And in order to stabilize the regret, we found it helpful to modify the objective slightly, where we take the max over several trajectories for the antagonist minus the average for the protagonist. And why this is good is it tends to keep the regret as like a positive signal and be a more reliable measure of, environments where it's possible to succeed, but they're challenging on average. The real regret, is the difference between the protagonist and the optimal policy, right? So this is just an approximation of it, and this helps us get closer to that approximation. And then the adversary is going to maximize the regret, and you can just have the protagonist and antagonist maximize their environment reward. That tends to work the best. Any questions about this before I show some results?
Yeah, I mean, I don't have a question, but I have something more like on scalability. I mean, what precludes you to apply this kind of algorithm to do some like robotic manipulation, right? Or like full robotic interaction on environment where like, automatically generate new environments or new objects to manipulate. So I keep learning better manipulation.
I want to do that. I think that's cool. The thing that precludes you, or the thing that makes it hard, is now you have to parameterize an adversary that can build objects.
Right.
So that's tricky. You need to build, you basically need to build an environment generating interface. Yeah. But we'll show that we end up doing stuff about that, and it tends to work. So, okay, so let me get into this.
Can you talk a little bit more about, I guess, the timing mismatch of information flow? I guess what I'm calling it, because the blue and red receive very dense signals, but the adversary does it on a different time scale, like episodic or something of that nature. So can you talk a little bit about how you dealt with that?
Yeah, that is tricky. We did find for like the different domains we applied this in, balancing the learning of the adversary with the agents is important. In the grid worlds, the agents learned pretty effectively and pretty quickly, and the adversary had a harder task. That actually worked pretty well because then the protagonist and antagonist scores were a more reliable signal of their actual ability. They're not just like randomly noisy. So what we've done in later work is if you pre-train the protagonist and antagonist, I think that could work better. You could also consider some of like the techniques from the GAN literature to like balance training of the generator and the discriminator to keep them balanced. We didn't end up having to do that, but it was something we were thinking about.
I also thought, what if you make an adversary that chooses from like a large domain? I mean, for the case of like self-driving cars and stuff. So just train an adversary that chooses like the worst example of it. You
could do that, and there were a couple of concurrent papers when this came out at NeurIPS. One was from Peter Abeel called value disagreement or something, curriculum generation, and they were saying, yeah, I have a pool of samples, a pool of tasks. Which should I choose? I'm going to choose it to maximize disagreement among an ensemble of value functions. So you could say, okay, I have a pool of samples. Which should I choose? Let's maximize the regret. Could be fine. Yeah.
Cool.
But then you have to have a predefined set of tasks, which, as I was trying to argue earlier in the thing, you might miss some tasks that are important. So I like the idea of having the adversary actually like construct freely a larger space of environments.
Yeah, but it might be hard sometimes, like, for like vision tasks. It's
Totally. Yeah. It's definitely that's definitely challenging. Other questions?
Yeah, I have a question. I was excited about the idea of maybe doing more and more and more complex environments. So maybe there's some kind of hierarchical, curriculum there. It's like kind of recursive idea, but that's all. I'm sorry. Not excited.
I'll show some results about that. So we do have sort of we do actually have a little bit of a hierarchical compositional adversary in one of the things we do. But okay, let me show the grid worlds. So I think this makes it kind of clear what the differences are. Like domain randomization, A, the environments are unstructured, and B, they don't adapt to the progress of the agent. Minimax does adapt, but as we saw, it can just make impossible environments. So paired is our Goldilocks. It's making these structured environments that are challenging, but not too hard, or not impossible. If you look at the results over the course of training, you see that paired on the left is the characteristics of the environment it's generating. So the passable path length is the shortest path lengths in an environment where it will be 0 if it's not possible to solve the environment. So you can see that like the Minimax population-based training is kind of driving that down towards 0, whereas paired is continuing to increase it. On the right, you see the resulting behavior of the agents in terms of the shortest path length in a maze that they correctly solved. And you see that paired is continuing to increase. What's neat about this is we didn't train the agents to solve longer paths or generate longer paths. This is just an emergent property of the algorithm itself. But the really cool thing is the generalization or the transfer results. So now we're going to test the agents pre-trained with each of these techniques in a series of human-designed environments. And what we see is that as the complexity of the environments increases, so does the performance gap between paired and the other techniques, where paired is generalizing much more effectively to these complex environments than something like domain randomization or Minimax. Yeah, so that's fun. I'll show the web navigation. So could this work on a better thing than grid worlds? I think this is a key question. We actually did end up applying it to this problem of having agents learn to navigate websites. So Google wants you to be able to say, okay, Google, buy me a keyboard, and it would go put your information into Best Buy and retrieve the keyboard for you, or book you a flight if you want to do that. And it was kind of neat to be hooked up with this project because, Google did say like, hey, you should try to have some product impact with your work. And it wasn't clear to me how these like multi-agent grid worlds were going to have that. But actually, this is a good problem because if you think about it, let's say I want to, train a flight booking agent for Delta, right? But we know RL agents don't generalize very well. So what happens if Delta updates its website? Does my entire system go down until I can like scrape the new website and like retrain on it, right? So if you want to be able to generalize, paired might be good. And the other thing is that what the team was doing before we started this project is they were literally hand coding a curriculum of easy, medium, hard, and hardest websites. And you can see that the agent is not succeeding on the hardest websites, even in their hand-coded curriculum. So we think, okay, let's do something better. Maybe this paired adversary could generate this curriculum of websites. And we actually did parameterize the adversary so that it can construct websites out of web elements. It can choose how many pages there will be in the site and what elements will be on each page. And you see that early in training, it keeps very few elements on each page. So it's kind of clear to the agent what it's supposed to be doing. Late in training, it's creating much more complex single form websites. So this is, again, emerging, not something we told it to do, but that's what it did. We tested them on an existing benchmark set of web navigation tasks, and we also proposed a new benchmark in the paper. And what we see is that our agents are, 4x more successful than the state-of-the-art prior work in web navigation. And actually, this paper proposed a modification of paired, which is more effective than the original paired. And it's eventually gets to like 95% task success across all these difficulty levels. By the way, the modification is just population-based training. So instead of having a fixed antagonist and protagonist, you can have a population and take like max minus mean of the population. But yeah, in conclusion, we think of unsupervised environment design as this formalism that can be useful for thinking about improving transfer and generalization. And we think of paired as very advantageous for this because constraining the adversary with the performance of a second agent ensures that it creates feasible yet challenging environments. And we think regret lends itself nicely to generating a curriculum.
Okay, I have a question about the web environment. So it seems like the adversary probably has a lot of discrete actions and multiple actions to generate. So I was just wondering how you optimized the reward and whether there were any challenges there.
Yeah, it's basically an autoregressive model that first picks the number of pages and then goes through each page and picks which elements. No, then for each element it says, should it be, no, sorry. Its action space is, here's all the elements and here's all the pages. And then it says, select an element and select the page. And it continues until it selects stop.
Okay, thanks.
It took me a while to cue that back up. Yeah, other questions about paired or websites or?
Yeah, could you describe the reward for the web page task, the web navigation task?
Yeah, it's just 0-1 binary task success. So but I think it does get no, I lied. It does get intermediate reward for entering some of the information. So if it correctly enters the name into last name, it'll get an intermediate reward, and then it'll get 0-1 task success if it entered all the information correctly. Yeah. So we actually found that did make it challenging. The 0-1 reward makes the regret signal quite sparse, which can be hard to learn from. And we found that in another problem as well. So in this paper, a key thing we did was also add a difficulty incentive to the adversary, which is we had the intuition that if you add more elements to the website, that's going to make it harder. So if the agents both succeed, then you are rewarded proportional to how many elements you added. But if they both fail, you're punished proportional to how many elements you added. So there's this additional difficulty metric that the adversary is receiving, and that helped a lot. Other questions? I do have some additional work I could talk about that's probably about 10 minutes long, but I also don't need to get into it if you want to just talk more.
So what's the next topic that you just mentioned? I was just curious.
Yeah, I wanted to talk about this kind of idea of paired is cool because we set up this very specific training protocol that we expected to induce nice behavior. But what if you're in the situation where you're not controlling the other agents that are in your environment? They just happen to coexist, and you might want to learn from them. So that's it's more relevant to something like multi-agent driving. There are other cars on the road, autonomous driving, sorry. There are other cars on the road. You don't control them. You don't even know if they're a good driver. What can you still learn from them in that situation?
Right. Yeah. I think for me could be also very, very interesting to know about the multitask, very complex environment. So not just achieving one goal or just getting, exactly one goal, but multiple goals over longer periods of times, where each of the agents has multiple things that need to do at the same time. So how they collaborate or how they compete, etc. in that particular environment, how these kind of settings might help for that.
Sure, yeah. I mean, this touches on that, especially the sort of latter work. So I can launch into this, but interrupt me if you still have questions or you want to talk about something else. It's no problem.
Maybe the last question I have, sorry, is about self-play, right? Because because how you put self-play, the research in this, if you have to compare with your line of research.
Yeah. So you can think about this as analogous to self-play, although I removed that slide, because the reason self-play works is that your opponent is always balanced at your current level of progress, right? And that concept doesn't exactly work for this adversarial environment generation because you and your opponent are asymmetrical. The adversary has a different action space than you, so it can just make the environment impossible. So what we do is we take a similar idea, which is that the antagonist is now the same as you, same architecture, and having experienced the same amount of training time and the same training samples, so roughly equivalent skill to you, again, we use that antagonism as a measure of what is the appropriate difficulty level for you at this time. But we just use it as a measure that informs the environment generating adversary.
And then the other question is, I'm sure have you thought about having like multiple antagonists that would correspond to different tasks?
Yeah, that'd be cool. That would be really interesting. We have thought about having a population of agents, but we didn't think of having like antagonist experts in each sort of like domain. That would be cool. Yeah.
Right. So that then become more like a multi-objective optimization problem, I suppose.
Right.
Cool.
So as you went through this process and you kept generating more and more environments that got harder, did some metric or some measurement jump out at you where like, I can see this is harder and I can measure it in some way, not just visually speaking?
Yeah, I think that was like a key thing for showing the grid world results, where we had an intuitive measure that we knew was linked to difficulty, which is like the shortest path length in the maze, right? And so that's an easy way to measure that, oh, something like difficulty is coming out. For the websites, it's a little bit less intuitive. Again, we use like number of elements added as a measure of difficulty, but that's not a super clear one-to-one mapping. Like more elements is always harder because like, as you can see in these pictures, you know, these early training examples, some of them actually have additional elements that the late training doesn't. Like it says like deal of the day, get it today, but it's just fewer elements per page. So it's like that we didn't anticipate that. That kind of came out.
Yeah, the reason I'm asking is like it could be very interesting to if this leads to the discovery of what makes things difficult, right? Because we all have our ideas about what a challenge represents or what can make environments challenging. But if through this process, you know, some insight comes from that, I think that would be really nice.
Yeah, I'm really interested in thinking about that. Like right now we're working on extending this to the case of language. So like generating language instructions. And I love the idea of saying what makes language difficult. Like if you're trying to follow an instruction, what makes it difficult? Right?
Yeah,
cool.
Yeah, that's interesting. Also, I think it would be very interesting if you put in consideration the knowledge of each of the agents. You know how much each agents know about certain tasks or certain for example, I was thinking about the language, but what happens if you use language applied to math education, for example, right? Yeah. So what's difficult is more conditional how much you know, how much you know how to apply, etc., etc., etc. So I think that might be interesting. That might be interesting.
It'd be cool to like have a personalized model that is tailored to the specific progress of each learner. Yeah.
Yeah.
So can I maybe be a bit, I don't know, doomsday? Like if for the web thingy, you basically know how to generate a whole bunch of bots that can fill out websites. Like, doesn't that create like a whole sort of thing where on the other side, if you're trying to evaluate it, you need to just kind of try to figure out what came from a bot, what doesn't. Like if you plug this into a system that is kind of like outside itself, what considerations come into play?
Yeah, I mean, that's a good question. We're looking at a pretty constrained version of the problem where we're basically doing form filling. So you have like customer information, you know the customer wants that information filled in, and then you just have to like do the mechanics of like plugging that in. Like let's put in this person's address, right? So you kind of can't do the task unless you have like legit customer information. But yeah, I guess you're saying like this technology could be used in a more adversarial way to like, I don't know, spam your congressperson or something. That would be bad.
I wonder if there is like an automatic way, like maybe like a meta way of generating the metrics for each of the environments. So on the grid, you choose, the shortest distance because you know the domain. But when it's not clear, maybe there is a meta loop that can, explore what kind of metric might be the best to apply there. Right?
Yeah, yeah. That would be interesting. I've been thinking a lot about like the generalization boundary, right? So like, let's say are you guys familiar with like Minecraft, where you have to like navigate an environment, but you have to like build an axe, use the axe to harvest resources, whatever. Like, it's quite possible that if you've already harvested a log, you can generalize pretty effectively to harvesting like a rock, but building a tool is like something you can't do. But those boundaries are quite flexible, right? So it's not clear like which task I should pose to actually hit something that you don't know how to do given your previous training experience. And the only way we have to like measure that right now is like, here's an agent similar to you that's trained on similar stuff. What can it generalize to? But it would be, yeah.
Yeah, that would be awesome. But I guess coming back to the idea to having multiple antagonists, right? Or
Mhm.
you know, so you specialize maybe in collecting one thing and then or doing other things, and then maybe it could be one idea is like, okay, what will you know, motivate to compose these tasks,
Right.
A multi-objective idea, or maybe having a different kind of agent. So now the metric is different because the metric now is compositionality, right? So doing
Yeah.
both tasks to accomplish another tasks, right?
Yeah. That'd be really cool. I think there's a lot more we could explore with that kind of building hierarchical tasks out of subcomponents that you've mastered, or like making a curriculum. We kind of argue we would do a bit of a hierarchical. We don't show this in the same paper about web navigation. We talk about like compositional problems where the adversary can choose like a set of the subtasks to make the full problem. So yeah, you could check it out if you're interested, but there's a lot more you could do with that.
But I think that will be incredibly cool because they definitely will be incredible general, right?
Yeah. Yeah.
That's very nice. Okay.
All right. Well, thank you for having me.
Well, this has been a very exciting
Thank you very
presentation.
much.
I wish we have more time with Natasha. Yeah, very, very excited. Thank you for taking the time, and thank you for coming to the Deep Learning Committee of Practice at Intel. Natasha, was great to have you.
Thanks. It was really fun.
Have a nice
Bye.
day, guys.
Bye.